All right. One, good. Good. Good to see everybody. So now we're doing sections 7.1 and 2 from the book. I also posted some problems for next week from the textbook, the first 3. You just have to compute the minima and classify them, like strict global minimum, local minimum. And I know also I added another book just to give you more problems, because I know there's not enough problems for you to practice. Some people asked me. So I added more textbooks, and I'm not assigning all the questions. It's just there's more places for you to do problems that are relevant to the course. Okay. All right. So yeah, tomorrow we have our Thursday we have our first quiz. I booked this room as well, so you can stay here if you want. You can go home and Google. So whatever you like, you can do. And yeah, so I haven't decided on which framework yet, CrowdMark, Gradescope. Do you guys have any preferences? I can go with. Is there one that you don't like? Like, do you hate Quarkus or do you hate Gradescope or? Huh? No, it will be, you have to write. Yeah, and you need to take a picture and you upload it. So I haven't decided on that either, because like you have a class and then you have the tutorial. So you might be like, your brain might be out. So, but of course you can like not attend anything and just come to the quiz. So, but I think let's do the first quiz during the tutorial just to see how people feel. What? No? Do you guys want a full tutorial? You prefer? Sorry? You prefer after? Most people want after? I don't care. It's up to you. Does you guys don't care? You prefer after? Why? No, but you won't be. Nobody will be supervising you. I'm not sure, but like I just feel that way. Like, I mean, when I say during tutorial, Etienne will go and I will be like waiting on Zoom. It's not like, but all right, we can do that. Let's do, okay, fine. Let's do the first one after, see if you are exhausted, and then we'll decide after. We can change back, doesn't matter. Whatever you're comfortable with, okay? So, oh, CrowdMark, but CrowdMark lags a lot, doesn't it? Well, it crashes and, yeah, it crashes a lot. I have so many nightmares from CrowdMark. Just typing on like, oh, help me. But I think I'll do Gradescope. I haven't heard problems in Gradescope. All right. Fine, let's start. So I'll do it after this question. Right, yeah. Is that too much? Oh yeah, we can take a break, of course, yeah. But then we'll go even later. Okay, fine. I'll ask you guys on Crocus. I'll do it. But yeah, I definitely will give you time. That's crazy. Yeah, there should be a break. You're right. Thank you. All right. Anyhow, so yeah, let's do a review of this stuff. Yeah, so you've done this in first year. So remember, when you have a function like x squared, okay, and you want to find the minimizer, what does you do? How did you find the minimizer? You just take derivative. So you have 2x and what? Equals 0, so the solution is 0. Okay, so we're going to do this for gradients. That's basically it. Okay, so the first few weeks are just review. Okay, all right, so what is an open set? Here's an open set. You have a guy like this. You give me any point x, and I can find the ball fully contained in the set. So is this point, can I draw a ball over here? Small enough? No, right? Because it always intersects the complement. So you always have to be inside. Okay, so and if you can do that, you're called open. So is this the set I drew? Is it open? Is it? No, because so you have to do it like this. Okay, so when you write things down or you give us diagrams, that's U and that's U closure. Okay, you put the boundary. Okay, all right. And when you hear the word closed, it just means the complement of an open set. Okay, I know there's other definitions, but we're just gonna go slow. So this is good enough for us. All right, and so what are we doing? We are gonna maximize a function, usually called cost or loss function, whatever area you're in, profit. And you have a fixed domain omega, okay? We're not gonna worry about omega yet. In our course, we're just gonna take it to be a nice convex set, which I will define next week. But usually trouble comes from omega when you go like in the, like other more applied problems, omega always gives you trouble because your data set can be very disgusting and you're trying to find minimizers on the boundaries and okay, that makes no sense. So forget what I'm saying here. But in our course, this guy omega will be very nice. It will either be open, it will be closed, or it will be closed or open, but with an unbounded component. So I might as well give you the main example that I had in mind, which is R2 positive. So this guy over here, the right quadrant. So is this guy open? Right? Just, okay, this is XY in R2 with X comma Y non-negative. Is it open? Zoom people, can you say open, closed, not open, nothing? Open or closed or nothing? Huh? So why is it not Zoom people? Neither, yes. So why is it not open? Well, can you give me, yeah, actually you should, yeah. So why is it not open? Let me wait. All the what? Oh yeah, sorry, yeah, yes. And why is it? Because if you take a guy over here and you try to draw a ball, it's not fully contained. It has stuff from inside and outside. So that's why is that okay? So take so no, because take 0, 1, right? And then we have the BR of 0, 1 intersects the complement, R2 negative. Okay? Does that make sense? Is it closed? That's trickier. And Zoom people, is it closed? Yes, no. Closed, not closed. Is it closed, Zoom people? It's like a different country. Not closed. Okay. So why is it not closed? Can you give me an? Oh, I might be asking too much. Damn. So let me define. Let me give you a better condition for closed because this is too hard for you. With the given definitions. So the one that usually take as definition is you give me given any sequence. So I will define what that means. Given any x1, x2, x3, so on in omega, such that when you take the limit of xn, it goes to some x in Rn, okay? If x star is in omega, then omega is closed. Okay? Does that make sense? Do you remember that? Yes. So can you now give me a sequence that will not, in omega, that is not converging to something in omega? Because we'll come back to it. I want to make sure that it's a basic example. Can you give me a sequence? Zoom people? What do you think? I need a sequence that is in omega, but converges to something not in omega. What do you think? Any guesses? So what? That's right, perfect. Even it's very suggestive, exactly. So this guy is the open stuff, right? So, but okay, does anybody have an example though? All right, I'll do it. Does anybody have one? Yeah, so infinity is not in Rn, so infinity is not in omega. So take xn to be n comma n. And this guy goes to infinity, which is not in omega. And this guy is in omega. Okay, so it goes like goes up to infinity. Okay, good. So it's not closed because it does not contain infinity, which is the boundary point of R2 non-negatives. Are the real closed? So we don't have infinity. So that's the problem here. Because you cannot do operations with infinity plus infinity equal to 2 times infinity is still infinity. So you get infinity is 0. So you have nonsense like that. Yeah. All right. So I mean, yeah, it depends what. Okay, I want. Yes, in some cases we say so. The reals, because that's a good question, are both closed and open. So let's not. Let's not go into this. Yes. So this is a little bit. I just wanted to understand that here you can have non-closure. All right. So why do we care about this problem? I'll just give you the 2 examples. So you can have some inputs. So let's say you have a factory, right? And you have x1 to xn, and the output is f of x1 xn. like a computer, right? So this is your output. And then you have a price. So let's say X1 costs P1 and X2 costs P2. But then when you sell it, the computer sells for Q dollars. Okay. What do you want to do? Yeah, what do you want to do? Why is this an optimization problem? Yeah, so like maybe silicon is too expensive, but I can still do it with like maybe people don't care whether I put silicon or plastic or it still sells because nobody looks into the computer. I can put tomatoes in it, nobody knows. So yeah, so this is the problem, and it tells you, okay, I have to buy X1 silicon, X2 plastic, and so on. And your omega will be, of course, our familiar guy. And that's, you're going to say it many times because we deal with real world quantities and they are non-negative, right? There's no negative silicon. Good. All right, question? All right, so that's one. Oh yeah, and we talked about this, so it's not open. All right, another problem that we will do in detail to this week. So this is relevant from statistics. You start with a data set, so you have some data points. So one of these data points is like xk, gxk, right? Let me make it very suggestive, like a sine function. And you want to figure out what the function is, okay? So you want to find g. G is not known. People just write yk, but you want to find g. Want to find g. What the hell? Yeah, so you want to find g, and you do a polynomial approximation, okay? So you want to find A0 to AN that best fits your data. This is called regression or quadratic polynomial fit. So here's again my function, and then it will be some polynomial that best fits the data set. Okay, so why is this an optimization problem? Because you want to minimize the error. So you want to minimize the distance of your sample data to the polynomial approximation by minimizing over the coefficients of the polynomial. Okay. And here you sum over all your sample points because you want a global approximation for all x. Okay. Does that make sense? If I just had this, you just give me a point and I'm done. I just pick it, I solve it. But here I have to solve, this guy goes to infinity in like applications because you have more and more data points. So this gets more complicated. Okay, so, and we'll explain why the square makes this problem much easier. Okay, and of course the picture is, if you just have some coefficients, you have bad approximations, but then as you add more, you have better approximations, right? That's what's going on here. Okay, questions? All right, good. Now let's start our semi-review. Local minimum at a point, it means you can find the neighborhood around x naught. So here's x naught, and this is the neighborhood epsilon, but you have to be fully contained in omega. Okay, that's the neighborhood. And for all these points, you need your f of x to be bounding it. So you have a local cone. So the picture is, here's your ball, here's your x naught, and locally, let's say this is your minimizer. Everybody else is on top of it. Okay, so you have like a cone. So this is, this is f of x naught, and this is f of x. Okay? Is that okay? What? I'm not Picasso. I'm just trying to like get the point there. So, okay. And yeah, this is the open ball. And maximum, from now on, we're gonna do everything with minima, because if you put a minus sign, you give me the maximum. Okay, so you can always flip. So that's why in optimization, it doesn't matter. We just look at minimizers. Yeah. All right. Do you have a picture? Oh, I have an example. Any questions? All right. So, yes, I might as well do it. So I want to find max and min. So what do I do from calculus? I take derivatives. So f prime is 2x squared minus 3x. Oh, yes, thank you. So then I take out the x and I have 2x minus 6. So okay, you already know what they are. Yes. What am I doing? Oh, yes. Thank you. And this is 6. And this guy is 0 only at 0, 2. Okay? All right? And but then you have no information. You don't know what this is. Is it global, local, maximum, or is it minimum? But yeah, I mean, in calculus, we'll talk about this later. You have to compute the sign of the derivative, right? And that's a pain. And we have to do the same here in this course. But anyways, my question is, so local minimum, can somebody tell me, can somebody give me the epsilon that makes x equal to 2 a minimizer, local minimizer? I mean, look at the definition, right? You have to find some epsilon so that you have this inequality. So what is the one for epsilon 2? Can you give me one value? And Zoom people, you can do it as well from the picture. Can you tell me a number that will work? Because you have to be careful, right? If I take epsilon 2 equal to 100, your minimizer goes like to negative infinity, right? The picture is goes like this. So wait, I want to see hands from now on, because I know you know it's very good. So yes, for epsilon 2 and epsilon 0, 1 is perfect. Because indeed, if you just look at locally over here, you give me any f of x. So I'll also write on the side. So yeah, f of x in b 0, 1, we have f of x will be less than whatever the value is, 1. And I mean for x. And then for x in b 2, 1, we have f of x. I should prove this. I don't like this. I like proving things. So x cubed minus 3x squared plus 1. Let's prove that 1 works, because I don't like this. So 3x squared plus 1. I have to prove that this guy is bigger than what happens at 2. So what is f of 2? This will be discussed. Huh? Okay, 2 times 2 times 3, 8, 3, 4 plus 1. It's disgusting. What? It's squared.
I mean, the coefficient is like with the what? The one that with of 2
It's 2 to the 3, so 2 times 2 is 4, which is 8. The second is 2 times 2. It's squared. Oh, there's a typo. Oh, yeah. Yeah. Welcome to my world. 3 times 4 is 12, minus 4. Okay, thank you. So I have to prove that this guy is bigger than minus 3. How can we do this? I don't think we can do this. We have to take derivatives. We have to do, there's no easy way, right? I don't see. If you see a way, I will happy to. Yeah, I have no idea. Oh, I can give you the other one though. So this one is easy. 3x squared plus 1. They're all less than 1. This guy, yeah, so minus 3 plus 1, which gives you because this k is, oh, you have to put 0. No, I can't do it. Oh yeah, I don't know. You have to do signs, you have to take derivatives. There's no easy way. I wish there was, but from the picture is obvious. Okay. I think you could have 3 to both sides and factor. I don't know. You guys can play with it all you want. I have to move. So, I mean, we will teach you ways to do this carefully. Like this is not carefully. Okay, but what about here? I allowed them to be equal, but you can have them not equal. You'll see what I mean in a second. So here we say that if you just remove the point, you have a local minimum. So the most easy example is just f of x equal to x squared, okay? And take x not to be 0. So if you remove the guy at 0, what do you have? You have f of x is equal to x squared. So if you give me any other point, you have strict inequality. So there's no other place where the function hits the minimizer. That's the point. A counter example is this guy. So go like a step function. Okay. This guy has many points where you hit the minimum. Okay. I mean, I can give you the function. It's just the line, step function, constant function, and then another line. Okay. So here, not strict local. Okay, put it here, 0, 0. All right. And the maximum is the same thing, you just take out a point. Global minimum, global maximum, you are not allowed to look at neighborhoods. So here this is perfect, the x squared. So again, the x squared guy is strictly positive when x is strictly positive, and this guy is f of 0, right? So x of 0 is a global min. Okay? Is that okay? Good. Strict global min. Add the strict too. We know even more. Okay, I'll make it bigger. Okay, questions? All right, I think we have all the definitions we need. Do I have an example? Right, yeah. So I don't know if you remember this. The infimum was defined as, I'm not sure. Have anybody seen infimum before? You've seen infimum? No? No, right? Okay. We might not have to talk about this, but I don't know. We'll see. If we have to come back, we'll come back to it. But the point is, I think we have an example here. So, right. So if you take e to the x, you have this amazing thing like this. And now look at the set e to the x, where x is in the reals, okay? What happens as x goes to minus infinity? Yeah, it's 0, but there exists no x naught such that e of x naught is 0. Okay, so that's basically all you need to know for this. That there are functions that have infima, so infimum of e to the x is 0, but minimum of e to the x does not exist. Do you understand? Because you never attain it. There is no x naught that will equal 0. You're always positive. No, I know you know. There's other people here. I have to make sure everybody. Because you haven't seen. Have you seen infimum in some other course? Okay. Anyways, the point is, when you are able to do this, we will talk about infima later on. It's a preview, okay? I don't know why I'm spending so much time on this. We'll come back to this. I just want you to understand that there are other objects out there. All right. Yeah, this is strict local minimum. Let me rewrite this. It's not clear. So strict local minimum. These are all local minimum, and this is strict global. Okay, it's global because if you draw a line under it, the entire graph is above it. Yeah. Okay, Zoom people, if you have a question, just tell me. All right, so that's the that's the situation here. Okay, so that's all you are going to see. There's no other phenomenon here. All right, now we have to go into classifying things. So remember, let's go back to our example. We had like x cubed 3x squared plus 1, and we find that x equals 0 and 2. F had a maximum and then a minimum. But how do I know that? I don't. I have to put it in Wolfram Alpha. Okay, but often our sets are very complicated. Numerics are almost impossible. So we need some local tools to figure this out. So the way we did it in first year is you give me a point just above 0 and just below 0. So take f of, I don't know, what's the smallest thing? What's something that will not kill us? Maybe a half. A half is okay, right? This is 1. I'll take a half. And this is 1/8. 1/4 plus 1. And can I make it bigger? Let me make it something crazy, like 100. 100 cubed and 100 squared. These are all positive. Okay, this is positive. Why am I doing this? And then f of 0 is 1, right? So what are we talking about here? I have to compare it to f of 0 at 1. So the question is this guy less than 1? In other words, you have 1 over 100. I don't know why I'm picking these disgusting values. Less than 0. And then you have 1 over 100, which is less than 3. True. Okay? I don't know, who cares? And then you do the same in the other way, minus 100. I don't know what I'm doing. And it will be, again, less than 1. If you do it, so yes, 1 is local max. Okay, so that's, but right. So how do you verify this? You have to take derivatives, which is very annoying. So you have to take f prime, you have 3x squared minus, yes, 6, thank you. Then 4x, and then x minus 4. Let me take out the 4. What? What? Yeah, this is, yes. Somebody's, okay, sorry. 3, and then this is, take out the 3, so you have 2, okay? And then you study its sign close to 0, right? I don't know why I took all this value. You guys should like jump in when I do stupid stuff, okay? So the question is, what does it do close to 0? So you study positive. So this is positive when x is positive and x 2 is positive, or x is negative and x is less than 2, right? So what is it saying? It says that when you're below 0, you're going up. Okay. And then if you flip all the signs, you get this guy with that guy, and this guy with that guy, right? Yes? Is that okay? Let me clean this up. So we're looking at positive. So this is the sign. Okay. So when you are below 0, your derivative is positive, but when you're above 0 and below 2, your derivative is negative, so it drops. I know this is a stupid example, but we'll come back to this for gradients. I mean, everything we do in multivariable will just be the same arguments. Okay. All right. Here you only have one direction. In multivariable, you have many directions. So that's why I'm trying to motivate taking directions. Here, you only have one. Okay. Zoom people, is it okay? All right. So in multivariable, you have a problem of direction. You don't know where to check that there's a bump. Okay. So anyway, so you'll see. We'll do it. Okay. So a direction is called feasible if here's the picture. You give me a point x naught, and a direction is called feasible if I can move in that direction without exiting the domain. So this guy actually works for any direction. But what about, well, I'll do the example right after. So here any direction works, but if you take your guy at the boundary, this direction does not work, right? Because the moment you move a little bit towards V, you're out omega. So if you move a little bit over here, X naught plus SV, this guy is not in omega. Just, okay? So this is called non-feasible. When you're inside, you can have an entire disk where you can move. So every direction is feasible. This guy is not because you're out right away. Okay. So let's do an example. So this is R2 non-negatives and take 1, 0 over here. Can somebody give me the feasible, can you give me a non-feasible vector? Huh? 0 minus 1. I knew somebody would say, okay, so let's do it one at a time. Perfect. I have them all together. All right. So your X naught is over here. And yeah, let's do this one first. So is that the one you said? Oh, yeah, okay, this one will work, yes. So X naught plus S 0 minus 1 is equal to 1 minus S. Is this in omega? For S, what? The definition is here. Is it in omega? Huh? Why not? Yeah. So it's not in R2 non-negative. Is that okay? I see confused faces. Yes. S is a real number. Oh, yeah, we could put S bar. It doesn't matter. If I,
I mean, so what does as for me? It's just that a real number bigger than that.
okay, how do you say it? This has to fail for every single, for every S non-negative. It fails. Like the moment you move to 0 minus, it doesn't matter what S bar is. It could be like the smallest number. I mean, just look at the picture, right? Zoom in. The moment you move in a little bit down, you get 1 comma minus S bar or whatever. But you're outside omega, right? Is that okay? Yeah, you just need bigger than 0, that's all. Otherwise, you're the point itself, and the point itself is in omega. So there's no content there. Is that okay? So to prove not feasible, you have to prove not there, not in omega, for every single S, not one S. Because of course, if you take it large enough, you're out. The point is it fails no matter how much you move. Is that okay? Yes. No, because S is strictly positive. Oh, yes. Yeah, I will fix it. Thank you. Ah, Where did I take this? Yes, that's a big problem. Thank you so much. Well, actually, okay, wait. Wait. Of course, when S is 0, you get X naught. Okay. So that's not, yeah, so that's not really, okay, how do we, you know what, okay, I'll remove it, she's right. I'll just remove it because it has no content, who cares? Okay, it doesn't matter. It adds no information. I'll just remove it. And it makes it confusing when you do contrapositive arguments. Yeah, like here. Is that okay? Good. Zoom people. No. What's the no for? This is no idea. I have to guess. Yes. Okay. I have no idea. All right, good. All right, good. You have to explain what the no means, Lucille. Okay. Oh, maybe I asked the question, and you guys can use your mic. It would be nice to hear your voice. But I will also check the chat. All right. So this guy failed. Do I have more space? I don't have space. I thought I had space. I will add space. Let me add space because I want to do it here. All right. We're not done. I have to do more. What about X naught plus S minus 1, 0? Can somebody give me, can you give me an S bar? Okay. Such that X naught plus S bar minus 1, 0 is in omega. Can you give me a, yeah, what's the sharpest? Yeah, just one, right? Because, where is it here? So you just evaluate the guy. So you have X, you have 1 comma S, what is it? Minus 1 S bar. Oh, no. 1 minus S bar, like this. Right? And to be in the set, you just need 1 minus S bar to be non-negative. So you get it exactly. Okay? But if I make the mistake and I jump too much, like, X naught plus 2 times minus 1, 0, I'm in minus 1, 0 land. And so I jumped away from omega. Okay? Good. 0.5. Yeah, 0.5. Anything less than 1. All right. And then the 1, 1, I'll let you check. It doesn't matter. You can put any number. Is that okay? All right. Now, let's see. What's the point of all this talk? Take F to be C1. We're going to do both directions. I'm going to do the easy one first. Namely that if you know your local minimum, then you have this. And then later on, I will do the other direction. So we do it one step at a time. This is called the necessary condition. Okay, so you know you're a minimizer, then your guy increases at every direction. So what you should have in mind is a cone, and this is X naught, and then just draw your gradient times V1 times V2. Okay, so when you do that, I mean, I shouldn't put the V1, you'll just get, but that's what I want to say. And it's, okay, so this is the coefficient. Okay, let me draw it bigger. I want you to see this because this is nice. So take a parabola, take X naught, and then pick a direction, V1. So like V1, and then project your gradient. So you have, this guy will be gradient of F V1 times V1, okay? This is V2, and this guy over here is gradient of F V2, V2. Does this notation make sense to you? Huh? Okay, good. So it says that because this guy is always positive, your gradient is always moving away from the local minimum. Is that okay? So we're going to prove this. And in fact, this will be a sufficient condition. If you have this increase, you're a local minimum. Okay. All right, let's go. Yeah, so as you move a little bit away from the minimum point, your function only gets larger. All right. Okay, let's do it. So let's take a break. You forgot what?
I forgot to enroll in the tutorial section, but I found this out today, but it's too late. I can do it on
Well, there's only one tutorial.
I think there are two tutorials.
Yeah, but there's one.
Oh, there are one.
Yeah.
So can you like click some like further links? But it's too late for me. Like,
But you don't, this guy, just use the Zoom link. There's no, I mean, nobody will care. There's no,
okay, but I
there's
think
no
it's like-
attendance or.
Oh, okay, so it's, I think there should be like some a name list or something like.
No.
Oh, okay.
Yeah, don't worry about it. It's fine.
Oh, okay.
Yeah,
So the tutorial is online or
online, yeah.
or there's no room there.
Well,
Oh, it's
I have the
okay.
room booked, so people can participate online through here.
Yeah.
Yeah.
Oh, okay. Okay, I see.
Yeah.
Yeah, but the quiz is online, right? Like,
Yes.
online form.
That's right.
Okay, so there's no need to come in person.
No, you don't have to. Yeah, of course.
Okay.
Yeah,
Thank
you can
you.
Google. That's right. Yes.
It doesn't matter. That's why I asked the one here.
Yeah, because otherwise there's no content. I mean, you can have it be zero. It's just we already know x naught is an omega. Yeah. So there's no.
But you're still.
Sorry, what's the question? Yeah. These are all the, yeah, all the extras. I mean, I don't want to get to like. I know, yeah, yeah, I don't know what to say. I mean, yeah, I don't know. Yeah, I go like, right, because I don't know, like in first year, some people say there's two types of limits. Like there's the DME, something like -1n, that doesn't exist. Like all this, but then you also have x and going to plus infinity. And usually like, and then we say that like this like exists. Like yeah, because it has a direction. So am I allowed to? You've seen this? Like I don't know, like take 10, like I swear. Like this guy, -1n and square does not exist. But this guy exists because he has a direction. So that's why I because like we will use this. For us, this would be like valid. Like it would be a valid thing. Like if this happens, I don't want people saying it doesn't exist. It's not. This doesn't exist. This does. I mean, I don't know, right? I will mention that right after when we start. No, she's right. I mean, you have to specify your topology. So, like in my topology, I want to allow limits. Yeah, but I get it defined myself because that's the topology, right? So I want the topology where this guy is defined to be converted, right? I mean, but I know, like this might throw you off. Okay, I didn't, did you take what you said? Yeah, did you do this with Alfonso? Like I thought in Alfonso, I remember he specifically said, make sure you split. Remember this? Like it was like Xn bigger than L or all n bigger than N, right? So that's why I was, but of course you go with what the right, the one you've seen. Like I will correct it, I will mention. All right. Yeah, let's start. Any questions? You prefer after tutorial? Okay. All right. Let's prove this result, which is basically from 1D, namely that if you give me a minimizer and you move away from it, you increase. Okay? You increase. So F prime is positive. All right? Just think of 1D. Whenever you get lost, go back to one dimension. So, okay, let's do it. Fix a feasible direction. Again, feasible means you're within your set. If you move a little bit, so X naught is not a boundary point, okay? And I mean, you could be a boundary point, you just have to make sure you point internally. All right. Anyway, so here's your function pointing in that direction. And you know your X naught is a minimizer. So you have this guy being, because X naught is local min. So so can someone tell me what S bar should be? So let me draw the picture. X. What should be the S bar? Do you remember? How do we define local minimum? Huh? Yeah, the distance. So this guy should be that ball we talked about. B epsilon X naught. This will be that epsilon naught. Let me quickly go there. So, right, we have this epsilon. Okay. So yeah, let me explain. So do I have one more? No. So what do we know? We know that f of y minus f of x naught is non-negative when y is in B S bar x naught, okay? That's by definition of local minimum. But any point in here can be written in the form y equal to x naught SV, right? So you give me this, you give me a point y. This point y can be written as x naught plus SV, where S is the distance of x naught to y. Okay, so I'm trying to explain the connection. Does that make sense? Is it okay? Is that okay? Over here. Is that okay?
Yeah.
Okay. All right, good. So that's how we get from local minimum to this statement over there. All right, and now we're going to compute G prime in two different ways. First, I use the limit definition. Okay, so this is just definition of derivative. There's nothing, no tricks. And we just proved this guy. So we use it over here. Oh, no. Over here. Is that okay? Is that okay? Okay, good. Zoom people. Now I'll compute it using, I'll ask you which rule. So remember, GS is this guy. So let me do it on the right. So you take DDS. So you have DDS of f of h of s. And so you have total derivative, right? Times DDS of h of s. No? So I read it. I don't know how you want me, how do you guys see chain rule? Like, I don't know, let me, okay, here's another way. I've seen it too many ways. Let me do it. Huh? What's the question?
How do you get data?
Oh, I just defined it over here, yeah. I'm just trying to, I don't know how comfortable you are with chain rule. So is this step okay? Do I have to justify it or can I just do it? It's okay, right? No? Okay, okay, I will just jump from now on. All right, so we computed it in two different ways and that's it, right? So we showed that this guy is non-negative, but is also equal to this dot product. So we have this statement over here. And it works for any feasible direction. So why is that? Go back to the picture. We had this picture, X naught. And because it's a ball contains every single direction. So I can move around. So I have all the feasible directions. And for all of them, I take S bar V to be a constant, epsilon. Right? In general, that might not be the case, right? It might not be a ball. It could be something crazy like this. In which case you have to pick your, you know, right? Let me do it in red. So your feasible neighborhood changes. It's just the distance from the boundary, okay? We'll come back to this. I just want you to have a taste of how to pick feasible directions. Here, we don't have to think about this, but in actual stuff, you have to take the distance from the boundary. Does that make sense? Okay, we'll come back to it. All right, let's do an example. All right, here's your function. Beautiful function. Just put up your hand, don't yell it out. So can someone tell me what's the first component of this gradient? Just the first component. Okay, you're like one person, everybody's like, okay, all right, what is it? Okay, I have no idea, I'll have to do it. 2x. Wait, can you repeat? Yeah, that's right. Good. And what about the other one? Good. We can take derivatives. Right. Okay, good. So why did I do this? No, I don't have it. Minus x plus 2y minus 3. All right, so do we have this? So I'm trying to find feasible directions, all right? And what is x naught? X naught is the origin. And I do it one at a time, all right. Yeah, so I have to compute this. Again, it was 2x minus y and minus x plus 2y minus 3 evaluated at the origin. So I get, yeah. And let's check the question. The question is, are there any V equal to AB so that 0 minus 3, so let me do it like this, TF at 0 dotted with V is non-negative. So our guy is 0 minus 3 dotted with AB, which is minus 3B. And you're asking this to be non-negative. Is that okay so far? So is this always true for any V? Can you give me a counterexample? Yeah, just give me one. So V equal to 0, 1 satisfies gradient of F times V is equal to minus 3, which is strictly negative. Okay, so what's the implication for X naught? What can we conclude from what we just proved? Is not what? Well, no, you can, omega is R2, so all the vectors are visible. Yes, perfect. X naught is not a local min. So this is that's a way to prove it. So if somebody asks you, prove me that this is not a local min, you just have to give them one vector where the gradient is negative. Do you understand? Because let's go up to the statement. The statement says if X naught is local min, then T of X naught V is non-negative for all V. Okay. Now, can somebody tell me the contrapositive? Does anybody know? Yes, good.
There exists to be such that gradient of less than there, yeah, implies that.
Well, no, X is not.
Okay.
Okay. That's it. So when somebody asks you prove me not a local min, you just have to find one vector V naught, concrete vector. All right, good. So now let's do it for the other one. 1, 2. So I have to compute this. So 2x minus y minus x plus 2y minus 3. Can somebody tell me what is gradient of 1, 2 at 1, 2? Yes, perfect. So this point was picked very special. It's 0, 0. So what can you say about gradient of f dotted with v? Always 0 for all v. Yeah, and we will prove next that so x naught 1, 2 is local min. Okay. Right. Oh, and that's a nice result. So here's a nice implication. First, we need the concept of interior points. So interior points. You give me a set omega. is defined as the largest open set. So do I have a picture here? No. So the picture is, let's take our usual candidate. Oh yeah, I forgot, yes. Good. So this R2, blah, 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 X, Y, and R2, X, comma, Y. So in this course, we would call it closed. Okay, and in other courses, they also call it. So this is a closed set using Euclidean topology. And when somebody tells you xn goes to infinity, you're free to say that xn is doesn't exist. Okay. I don't know. I mean, if you took Alfonso Course 137, he told me to never write this, but that's what we're working with. In Euclidean topology, you're not allowed to go to infinity. Okay. So if you have xn going to some point x naught, and this guy is in R2, this guy, then you can also get that this guy is there. Okay. So it is closed. Okay. All right. That's just a comment. And but then we want its interior, and that is simply R2 strictly bigger than 0. Okay. So x, comma y, so that x is strictly bigger and y is. Okay. All right. And it's the interior because if you give me any point away from the boundary, I can draw a ball around it. So let me give you a proof. Because we're going to work with this set a lot. So give me a point AB, take the distance from the boundary. So then consider the ball B epsilon AB with epsilon equal to A squared plus B squared divided by, what's the smallest? So I need this and I need this. So take the smaller of the two and divide by 2. Okay? Do you understand? Is that okay? Because it will be this guy over here. So I just proved, so this is the proof that R2 strictly bigger than 0 is open. So take any AB with A comma B positive, and then epsilon equal to AB over 2 works. So this will be inside. This will be inside R2 strictly positive. Does that make sense? Is that okay? Okay, good. Yes, question. Oh, this is called the minimum, and you haven't seen it, so I'll just write minimum. Yeah, it's called the wedge. Okay. Magical thing. Zoom people, question? All right. Oh, there's also V, which is maximum. Yes. All right, good. So that's an interior. And can somebody tell me what's interior of 0, 1 closed? Yeah, I know. Is that okay? You just remove the boundary points, right? What's the interior of? We just talked about this. Is R2 strictly bigger? And what's the interior of the unit ball? Can I see hands instead of people? Can you put up your hand? Yes, because like I want to ask other people too. Any ideas? I want to see if people understand. Yes. Without what? Huh? What? Yeah. But I don't know. Maybe I'm being too pedantic. Yeah, you just put strictly less. Yeah. So, all right. This is not a hard course. Don't don't worry. All right. Okay. All right. Okay. Yeah, that's a nice result. You saw it in first year. Take a guy from the interior of omega. You're not allowed to go to the boundary because the derivative might not even be defined. So that's a whole other story. But suppose you're a local minimum, then your derivative is zero. Of course, you've seen the other direction, and I will prove it. But yeah, that's what we're gonna prove, right? That's how you find local minimum. You set zero to find them, right? Yes, good. Any comments? No comments. All right. Right, it's in the interior, so you can draw a ball around it. So you can move in any direction, okay? You're free to move however you like. All right. Jump too much. So we just proved the result that if you're a local minimum, this guy is non-negative, okay? For all feasible directions. But here, all directions are feasible. So you can just write this for all Rn. Is that okay? It's a dirty trick. I want to show you what the trick is. So now, since it works for all V, take minus V. Okay, you also have that when you do it with minus V, it's also non-negative, right? Can someone tell me how to finish from here? Hopefully I don't answer it. Yes, so how do you finish from here to get that the gradient is zero? It's a sophisticated argument. I'm not sure. Maybe I'm asking too much. Yes. Yeah, but you don't need C2 for that. So yeah, so let's compare the two, right? Dot product is linear. So you have minus dot FV bigger than zero. Move it. Okay, but you also have this. We're not done yet. I think we will use the continuity right now. So from here you get dot FV is zero for all V in Rn. And I want to prove that the df of x naught is zero. How do I do that? Yeah, you can go ahead. So what do I do? How do I use continuity? Do I need continuity? Huh? Sorry? Discrete? Oh, no, you guys are complicating it. What's a good choice of V that will give me this? You just have to tell me what V to pick. This is one V. Huh? Sorry, what? Yeah. So just take V to be itself, the gradient. Then you have, is that what you said? Oh, what is, oh, damn it. I put too much faith. I thought you said that. Sir, I should pay attention. Huh?
That's arbitrary.
Yeah, but here, we proved it for all of them. We proved it for all of them, so I can just take one of them. And this guy is 0 by this, right? But what is this? This is the this guy. But this guy is a sum of numbers. Okay? And that means that each one of them is 0. So it means the gradient is 0. Is that okay? It's okay, right? Zoom people? Oh, add both inequalities. Yes. Can you guys use the microphone? I want to hear your voice. Okay. I have to check. All right. Yes. So that was the. I don't know why you guys said continuity. Why do you think we need? Like, what would be? No, I'm not saying for all x. Like this guy is a fixed vector. Yeah, but oh, I see. Yeah, locally. Oh, yeah, this. Okay, we'll talk about this. Yeah, you'll need. But for now, no, it's just one vector. All right. Let's minimize this function. Looks almost the same. Is it the same? No idea. This guy is open. Let's not. We talked about this. Whatever. So to find the minimizers doing the contrapositive, you just have to find the zeros of this gradient. So you equate components, right? So this is second year stuff. And here's your system. Okay, I solved it for you. And we get 1 and 2. All right, unique solution. Okay. What else? Oh, yeah, but right. So, but we cannot tell what this point is. It could be a maximum, a minimum. It could be neither. Some saddle point. Who knows? We'll come back to this. So, but yeah, this would be a global minimum. And here's how you do it. This works sometimes, so it's good to see it. It's called quadratic form. So we had this crazy function. I'm not going to write it, but it's called completing the square. Okay, you can look this up. This is a formula for it. And you can write it in this form, which is a difference of, you have squares with a constant. And we'll talk about this next week. Whenever you can do this, you get a global minimizer. So whenever you have a convex function, like things that look like this, plus constants, you have global minimizers. And we'll prove it that it's if and only if. You have a global minimizer, if and only if you can do this. All right, and you can see it from here that the minimizer is at 1, 2. Can you tell me why? When is this the smallest? Huh? When is this quantity on the right the smallest?
I believe it's when the squares are 0.
when they're both zero, right? So this guy is zero when it's two, but when this guy is two, you get also zero, so you're lucky. Is that okay? Zoom. All right. I have some MATLAB pictures. I want to give you the code. I'll put it on Quarkus. So this is that function over there. And the guy in the inner circle is the minimizer, 1, 2, as you can see. And yeah, global minimum. But yeah, you don't want to do this. You want to do it mathematically. This is too much work. All right, here's another example. So I compute the gradient. This is the gradient. And then what? Oh, this is going to be disgusting. I remember. So, okay, let's do it. What's x naught? Oh, we don't know. Yeah. So we have to split cases. This is disgusting because when you're on the boundary, only you have finitely many feasible directions. Not finitely many. I mean, you have only a portion, whereas here you have all possible choices. So when you're internally, we can use that condition we just talked about. Right? We had this equaling 0, x naught local min. But it has to be in the interior. This condition fails at the boundary. On Thursday, I will give you the example. I will give you an example where you're not a local min, but your derivative is 0. Okay, so you have to be careful with this stuff. It's not if and only if. Okay, but when you're in the interior, you're good. Here you just set it to 0. And yeah, I will do it in the next slide, fine. When you're on the positive axis, yeah, which is that, sure. Then you have you can only check only these guys are feasible directions. Let me draw the picture again. This is the x-axis. Take x naught over here. And V1 can be anything. But V2 needs to be going internally. Okay, remember the set is this guy, right? So to stay in the set, V2 has to be pointing upwards. Okay, I'm just going over, I'm just going over the feasible directions. That's all, I'm not doing anything. I will do the computations after to find the x naught, but first I have to know where can I compute my gradient. Yes, so anyways. Now, the claim is that this guy is non-negative. Okay, so let's do that. Yeah, let me do it. So what do we have here? Y naught is 0. And this guy is like this. And you dot it with V1, V2. So this guy over here will be what? 2x naught minus 1 V1 plus V2 1 plus x naught. Okay. Yeah. So so to have local minimum, we will need this to be increasing, which is clearly not always true. Just take x naught, just take this guy to be something negative, right? So not every direction. So again, let me repeat. I'm going over each feasible direction and I'm requiring this to be non-negative because that tells me that the gradient increases, okay? But here, when I do this, it fails. So it means it has no local minimum on the positive x-axis. Because I can always pick V1 and this to be negative. I can make this whole thing negative. For some V1. Okay? Is that okay? We'll talk about this in a second. So another possibility is you're on the y-axis over here. And here you can only move like this. So you can move up and down in V2, and V1 you can only move internally. That's the feasible direction. And to have that x naught is a local minimum, you need this to be non-negative. Okay? I know I keep preparing myself, but I just want to make sure you understand.
Sorry, for the minimum on the
And we'll
x-axis,
show that these two fail. Okay, you cannot have them on the boundary. All right. Questions, Zoom people? There's one more, right? Yes. And then finally, you have the origin. And to be a local minimum, you need it to be non-negative. And in this case, you need both of the vectors to move. You need both V1, V2 to be non-negative. Okay? So these are the feasible directions. Okay, so let me repeat. You will be given a set omega. You have to find all the feasible directions, which I did, for every possibility. Okay? Because they have different feasible directions. And then on the next step, I check which one of them is true. Okay, some of them will not be true, which means that they have no local minimum. This will not be local minimum, this will not be local minimum, and the likes. You understand? All right, let's do the computations. Case one. Here in case one, I'm setting this to be 0. Okay, so I will solve it, so don't worry. So we have 2x naught minus 1 plus y naught, and then 1 plus x naught equal to 0, 0, right? And you get a system. You get x naught to be minus 1, and then you get minus 2, minus 1. So you get x naught is minus 1, and y naught is what? Yeah. So, good. Is this a local minimum? What? It's not. So you know why? So, I mean, okay, it depends what your domain is, right? So, minus 1, 3 is not in R2 non-negative. That's all. If omega was R2, then yes. But it's not. Okay, we're just talking about omega, like prices of silicon. We're not talking about negative numbers. Good, perfect. So case one is easy. Case two, to have a local minimum, what was case two? X-axis, okay. So to have a local minimum on the x-axis, you're asking for the gradient to increase along all the these directions. That's what it means to be a local minimum at the boundary. Okay. So we do this. I plug all the gradient stuff. But here's the problem. You can pick any number you like. I picked V2 to be 0. It gives me this. Okay. Okay. Which gives me this equation, because I can just take V1. Yeah, it's true for all V1. So how do you say it? Take V1 to be negative. So the only way for this to be non-negative is for this guy to be 0. So let me write it out. So why does it imply it? Because take V1 to be the negative of 2x naught minus 1 plus y naught. Same trick as before. That gives you that minus 2x naught minus 1 y naught squared is non-negative. But when is this true? In which case? When what? What? Yeah, when it's exactly 0, yes. All right, good. Doesn't the case for the x-axis depend on x naught as well? Yeah, it does. There's an x naught over here. 3? What do you mean 3? Okay, so right, y naught is 0 because we're on the x-axis. You solve it, you get x naught to be a half. So then we have, yeah, we have a minimum point over there. Good. Anyways, we'll talk about this later. These are all candidates. I'll talk about it. All right, now I'm going over the y-axis. Again, to have an increase, you need the gradient to be increasing, dotted along the feasible directions. Okay? All right? You're not allowed to look at other feasible directions. Good. All right, so wait, too fast. Again, I just want to find a candidate. I don't care about all of them yet, because we will do this later. Take V1 to be 0. You get the system, same trick as before. Set V2 to be minus 1 plus x naught. This and this give you this, which gives you x naught to be minus 1. Okay, so you have another candidate, which is the, so you're over here, and then it's, what am I looking at? X-axis, right? What is case 3? Confused. Y-axis. So why am I, no idea what's going on here. They got mixed. So this is x-axis. Anyways, it fails regardless. So in fact, x naught is 0. So this is all complete rubbish. So yeah, you have no minimizers. Yeah, which is not in our domain. It's also a contradiction. So there's no minimum on the y-axis. Okay. All right. Okay. What else? So maybe I should explain this argument more carefully. To fail to have a local, remember we have this local minimum contrapositive statement. It was if you find V star so that gradient of f V star is negative at x naught y naught, then x naught y naught is not a local minimum. Okay, so here what we did is we picked a V. So our V star will have V1 equal to 0 and in fact, my V2 will be minus 1 plus x naught. And so, yeah, it fails to be a local minimum. I don't know, there's many ways to do this. All right, let's do one more. This is the origin. So I compute it at 0, 0. Okay, so this guy is equal to minus 1. This guy is equal to 1. So you have minus 1 V1 plus 1 V2. Okay, happy? Yeah. And in order for this to be in order for the origin to be a local minimizer, you need all the gradients dotted with V at 0, 0 to be non-negative. Again, this is because to have a local minimum, you need your gradient to be going up, to be positive. This is your derivative. Okay? All right, and this gives a problem. So, so here's the, right. So I just have to disprove it for one vector. So again, remember your condition. A point is not a local minimum if you can find a feasible direction on which your gradient dotted with V is strictly negative. Yes? So, yeah, so I'll do it by hand, it's fine. So we have a gradient of F at 0, 0, dotted with V1, V2. And this was minus 1, 1, right? Dotted with V1, V2. Take V2 to be 0. And I don't know, take V1, it doesn't matter, it fails right away. V1, and this guy is strictly negative. Do you understand? So gradient of F at 0, 0, dotted with V1, 0 is strictly negative. So 0, 0 is not local minimum. Okay? To prove local minimum, it has to work for every direction. To prove that is not a local minimum, you actually have to find one direction that it fails. So I found one vector that is strictly negative. If you want local minimum, you have to have it non-negative for all V. All right. And yeah, whatever. We'll continue Thursday. Thank you.
Hello, hello. I don't believe you can hear me. I'll just say some digits of pi, maybe. Maybe it's, oh yeah, yeah, okay. So people can hear me, I think. That's nice.
Yeah, thank you. Just serious. Can you try again?
Hello, hello.
Yeah, yeah. I'm sorry. Just give me a second. Okay, can you speak now?
Can you hear me? Okay, okay. Sorry.
Now I can. Can you speak?
Hello?
Yes, 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 I can hear you. Please, nobody told me.
Oh, well, I don't think anyone tried to talk
Oh, okay, okay, okay.
so far.
Is it going okay so far? Can you communicate and post questions and everything?
Usually I don't have many questions, so it should be fine.
Okay, but can you please feel free to use the mic?
Yeah, yeah, yeah.
All right, thank you.
Have a nice day.
Okay, bye. Yeah.
So just to confirm, the first one has the interior zero.
No, 01. Did I say 00?
Oh, shoot, no, it's my bad. Yeah, sorry, because I missed this part.
Oh, okay,
Yeah, sorry, why would I read 00? My bad, yeah, 01. So like this one is just the slide.
yeah, you remove the boundary key.
Okay.
Yeah. Yeah.
You mean like the quiz questions will be similar to the ones you posted?
Well, similar. I mean, if you do them, you will do well. Like if you know how to do them very well, I will change the question, obviously. Yeah. Yeah,
It actually requires quite a bit of computation.
it does. Which one? Can I see? Oh, yeah, never mind. No, let me find it. Wait, let's do it. Oh, I see. It's like a Taylor thing. Well, I don't know. Wait, what is it? What's the problem? No, who's your mouth? Who cares?
And the movement alpha actually spits out like this very
No, but you have to evaluate.
Yeah, to plug in. There's just so much of plugging in. So many different ones.
Yeah, let me discuss it right now.
Yeah.
Well, I'm not gonna say, I don't know how much time you have anyhow. It's like, okay.
How long will it?
Well, I'm trying to decide now. Like, what do you think is logical? What do you think?
Not sure. I
It would be like, it would be one question with maybe 2 parts or something like that. But then, I don't know, like,